Hi guys, can I get a sound check?
Yeah, we can hear you.
Great, thanks. Um, Sorry guys, my dog chased me out of my office because she was barking so much up front of the house, and now I'm like back here and she's barking that the dog's back here. So I don't know what to do. It's either the dog or you guys, and you guys may just have to go. Just kidding. All right.
What type of dog is it?
It's like, it kind of looks like a small coyote. Oh, so I have two dogs. So I have an English bulldog, and that one is just like the very definition of like a couch potato. It's like an English bulldog. It's like 50 pounds and it's only yay big. I just perpetually angry looking, but it just does not bark. Doesn't do anything. Just sleeps. And then I got this one, and this one is like some kind of a weird mix. I think she's got, God, I forgot what you decide she must have. I'll invite her over one of these days as a guest. But yeah, small coyote. She looks like a small coyote. Okay, guys, let's get started here. And so where we were talking about was now with all the transistor definitions or the functions of the transistor, as you know, we have the essentially the most important thing is this voltage versus current of a transistor, and we had two different models. One was I think it's called the Shockley model, but the first level model. Where we had these these are VGS, high, mid. And then we had sort of the way it really works, which was kind of like, they had these upgoing things, and the current wasn't going to be as high because of, electric field effects. And the effective, the channel length modulation and things like that. But the upshot is we have this V drain source versus ID type of models, and now we want to use that to figure out how a CMOS gate works. And like I mentioned, the inverter is our proxy to all things, all CMOS logic gates, because as you'll see, if we look at the inverter, we can kind of use the same thinking to look at a NAND gate or an OR gate with a little bit of complication. Okay, so what do we do? Well, the way you'd analyze the circuit, this is our inverter, is you have input going to these two. Remember, the gates are purely capacitive, so it just looks like there's no current, leakage aside, etc. Which leakage doesn't really, the leakage current, etc. is really for when the transistors are off. they're really much smaller than any on current. But besides that, basically the only current you get on the output, and also your load is capacitive. So the only current you have on the output are the currents of the drain source currents of the P and the N. So basically you have, you know, these currents, and you basically, the way you look at, you want to find out kind of a couple of things about this gate. One is the transfer function. So that is V in, V out, or what happens at, you know, low speed, say, or whatever. What's the, how, remember inverter transfer function was like this. When the input is low, the output is high. And when the input is high, the output is low, like you would expect for an inverter. So we want, you know, basically it's got a simple equation, V out. So 0 VDD and VDD 0 or 0, 1, 1, 0. And then the other thing we want to find out, so this tells you how much noise margin you have. You know, are your logic gates susceptible to power supply noise and those kind of things. By the way, I was looking this up for my other class. So the latest, this is blue. I get, you know, I feel like I'm kind of gotten blasé about this stuff, but it really blew my mind. So it said the latest NVIDIA chip in that, it's called the GA100 Ampere. I don't know if it's used for gaming devices or what, or for servers, but it has 54 billion transistors. Okay, so 54 billion. So all those, they're all not switching at the same time, but even if a small part of those things are switching, they're really gonna disturb your power supplies. So one side of the chip may be switching a lot. It could be pulling the power supply up and down. We'll see in a couple of lectures how much that could really be. It could be a lot. But you know, if you guys ever, like if you have a FPGA, Xilinx FPGA board or something like that, with some significant amount of switching, it doesn't even have to be that big. You just take your oscilloscope probe, see if you can, I mean, I don't know if you can find the power supply, but if you put it on a power supply, you won't see a straight, flat 1.8 volt or 1.2 volts or whatever it is. You'll see this guy going crazy, fluctuating, depending on what the chip is doing. So that's the importance of this sort of a transfer function from a noise margin perspective. You know, it's really, really important to have a lot of noise margin. And then the second thing is trying to figure out like how fast is this device going for a certain transistor size, for a certain load. So the second thing we need to use these models for, to try to come up with some estimation models, is the transient response. So that means if you have this, you know, this inverter, say, and it has a, you know, low to high going signal, how fast is the output switching from high to low, say. And we basically use the same, we're basically looking at these drain source currents versus input voltage change to estimate both of those phenomena. Okay, so we're going to look at the DC response first. So we're looking to calculate this transfer function, something like that. So what we do is, again, there are no other currents. So all we do is we do, you know, Kirchhoff's current laws. We have two currents, one of them the P drain source current, the other one is the N drain source current. And we set those equal to each other, at least in absolute value, because they're going in different directions. And you figure out, what is as the input changes, how does the output voltage change? You could do that by, just having, using a bunch of equations. Remember, if we use this to simplify equations, we would have, say for the N, well, I think we're going to see this in the next slides, but basically you have, the thing could be in cutoff, could be in linear mode, could be in saturation, and each one of them has, a different current equation. Okay, so we could set those equal to each other, but one, it gets pretty tedious because it's like basically you're setting these equations depending on where your input is and where your output is. You basically have to select, whether the N or the P is in saturation, linear or cutoff, and then you have to make those currents equal to each other and solve for V in versus V out. So, that gets kind of tedious, and it doesn't give you as much insight as using a graphical approach. And what a graphical approach is basically a load line approach. Okay. The first thing you'd want to do is figure out, depending on what the inputs and the outputs are, what operating mode these different devices are in. So let's take the NMOS transistor in an inverter. Okay, so you have, basically let's start with the different modes here, right? So we're just looking at the NMOS, this guy here. So for an NMOS, it's cut off when the gate source voltage is less than VT. And I'll say the VT of the N-type, the threshold voltage of the N-type device to distinguish it from the P-type device. Okay, it turns on either in, so these are both on. This is off. So on, for it to be on, it has to be, the gate source voltage has to be higher than VTN. Okay, and then if you guys remember, draw the drain source versus the drain current, we defined the linear mode when the drain source voltage was less than VGS minus the VTN. So that's what that is. VGS minus VTN. Okay, and it's in saturation when VDS is greater than VGS minus VTN. Okay, so we know all that just for the NMOS transistor now. So just looking at this device, we have, these are the parameters we have. We have V in, we have V out, right? We don't, we're just to, once you guys take a few minutes, so, here, 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 here. Basically, we write these equations. It's pretty simple for the NMOS, just in terms of V in and V out. And this will help us, this practice will help us in a couple of slides. Once you guys take a couple of minutes, just try to do that. So just rewrite these equations in terms of V in and V out. Okay, guys, so let's try that. So basically, if we just look at the NMOS, the input goes to the gate of the NMOS. So that's the gate voltage, and the source is ground. So Vn, or I should say VGS, and is just equal to Vn. Okay. And the drain source voltage, VDSN, so the drain just goes to V out. Okay. And the source is ground again, so that's just equal to V out. Okay, so all we have to do is to then substitute that here. So if Vn is less than the threshold of the N, this guy's less than the threshold of the NMOS is off. If Vn is greater than threshold of N, it's on. It's on. And then if V out is less than Vn minus the threshold of the N, it's in linear mode. And if it's V out is greater than Vn minus V threshold of N, it's in saturated mode. Okay, so that's for the NMOS. And then for the PMOS, we can do the same thing, right? If we just look at, we don't look at this for a second, we just look at this guy. The only difference, and this gets a little bit trickier, is notice that gate source of the PMOS is Vn minus VDD. Okay, this is important when we do the load line. So it's Vn minus a VDD. And then the drain source is V out minus a VDD, because everything's getting referred to this VDD, whether you're talking about gate source or drain source. Okay, so that's what we have for the PMOS. And if we draw now, if we again, we could just pick the nodes, write the current equations, and try to figure that out. But that's, you know, you'll see how much easier and more, I think, more meaningful it is to do the graphical mode. So the first thing you do is you draw. Hopefully, you guys can read this, but basically, we've got the voltage. So the VDS versus current for, you know, the N for different gate source voltage values. And then on the same graph, we've got the IDS curves. It's going negative. The current is going negative because you know, it's flowing in opposite direction to the drain source of the N, and these voltages are going negative because the gate source is referring to VDD. So you get your highest current when your gate voltage is at, say, at 0. So you get the highest value from highest difference from VDD and that. Okay. So first thing you do is you draw those together at the same time on the same graph, say, and then you can. And in this case, we've made the PMOS wider because if you remember, we said the mobility of the P, the mobility of the N is, we said it's 2 or 3 times the mobility of P. Because of velocity saturation, it's kind of, they get a little bit closer together, but for the most part, what we're going to assume going forward in these sort of hand calculations is that the mobility of N is about twice the mobility, or exactly twice the mobility of basically. Again, it's just for hand calculations. And that means that the beta of N, which if you guys remember is mu N Cox W over L, if the width and the length of the N, so if Wn over Ln is equal to Wp over Lp. So the width or length of those two devices are the same. If that's the case, then beta of n is twice beta of p. Or the other way to look at it is if you want to have them have the same current gain or the same current for the same voltage, you would make the width of the p's twice as wide as the width of the n. So for beta n is equal to beta p, width of p is 2 times width of n. Again, these are like, you know, for every particular process, those numbers are going to be different. But again, for our analysis today, and you know, for what we use in the class, like these assumptions, we are going to use kind of that. Okay, that we're just going to assume that for the same current, the PMOS has to be twice as wide as the NMOS. Okay, so if we do that, these curves are going to be exactly, the N and the P curves are going to exactly match, and they're going to be opposite polarity, both in current and the voltage, with respect to each other. So now if you do a load line analysis, what you'll be doing is you're going to do so we're going to plot V out versus I guess I out is the way to look at it, okay? So, so what you'd have to do, if you remember, or let's go back, oops. Yes. Okay, so here's we had, you know, we had the N, but I did a really bad job of that, and the P as a function of the N, the VDS, and the P PVDS, and you know the different gate source voltages and currents. But if you make both of those equations, if we want to just draw it in relationship to V out and I out, and I'm going to call I out the current going sort of in or out of this node, this V out node. Okay, so if I want to plot that, well, it was pretty simple. I don't know if you guys remember a couple of slides ago. Or was it? Here, we just said, you know, Vn is VGSN, and V out is VDSN. And the current is, you know, I out is IDSN. It's the same polarity. So if we go back here, we end up with the same curves we had sort of out here. So these curves, these curves here stay the same. Okay, so that's for the N. Okay, so for the P, V in, V drain source of the P is V out minus.
Professor, can you hear us?
Yeah, I can hear you.
Your screen is not sharing.
Oh, thanks. Thanks for letting me know. Let's see what we got. First one. Okay, where did I lose you guys?
I don't think it was too long. I think it was like a couple minutes.
Okay, did you guys see this where I was doing, whoops, shouldn't have done that. Thank you. So basically for the N type, so for these curves, if I do a load line, so for these guys, for this N stuff, V out is the same as VDS, and IDS has the same polarity as I out. So if I draw V I out versus V out, it's going to be the same curves. Okay, so that's for the N. But for the P, the drain source of the P is V out minus VDD. Okay, and we talked about if you want to put it in terms of the current of the P with respect to I out, we had to pick a polarity. We picked the polarity in the same direction as the current IDS current as the N. So basically what we would have to do is basically plot, if we're going to plot, so this is what we want to plot, I out versus V out. So to put the P here, we would have to we would mirror the currents up here. So the P currents will look like this. Okay, mirror from here to here. And then we would shift to, again, put it in terms of V out. If you'd made this V out, you have to shift these curves over by VDD. So basically what we end up with the P curves is they look like this. So again, because the relationship between I out and IDS-P, they get mirrored, the current gets mirrored here, and then we subtract or add sort of VDD to it. So we end up with, sorry, this being VDD to 0. So to create a load line. Okay. You guys good with that? Everybody kind of understood that? It's always hard to draw the load line, but basically you end up with these curves. So again, I'm drawing the way I look at it is this is I out. So DSN, an absolute value of DSP, and this guy is V out. So the V drain source versus for the N stays the same. So those all stay in the same direction. But the drain source of the P, you have to add VDD to it to be the same as V out, and it gets shifted over from this side to here, and then you get the superimposition. Any questions about that? I always get a little confused about load lines myself, but that's what we're doing.
Nope, no questions.
Okay, great. So so the way we would look at this, okay, so we plot this thing, and for each V in, sorry, for each V out, and you end up in a place where the V ins are the same, okay? In other words, if you have for the same V in, so let's say V in, so this is V in equal to 0, right, for the P, okay? And so the V in 0 for the N is over here. Is this guy, there's no current on the N, but the P has a lot of current when you're at 0. Right? It's got this thing. So where these things meet, which is like in this case is out here, is where you say is my V out. That's where it must be. So if you do like sort of a, let me see if this has an animation built in here. If I can get it to play. Okay. So again, in the case where Vn is equal to 0, okay, that's the blue, when Vn is 0, the PMOS has a lot of current, right? So it has that VDS or versus IDS curve. And Vn has 0 current. So where they meet is at VDD. So when Vn equal to 0, output is at VDD, which is as a starting point good news. Okay, let's say Vn gets a little bit higher, or 0.2 VDD here in this case. See the current of the PMOS drops because its gate source voltage is dropping, so its current is dropping, but the NMOS hasn't turned on yet, so it's still down here in the 0. Oh, good, I can mark this. 0. So they still meet close to VDD. It's essentially VDD still. Okay, now we got the case where the N, you see the N is waking up. Okay, so where Vn is 0.4 VDD, and the gate source of the P has gone down further. So where they meet is, still close to the VDD, but now you're starting to get a little bit lower than VDD. So if we like, so if I was gonna do this, so we started here. So this is Vn, this is V out. So it was kind of the case where when we were at 0, Vn was 0, V out was VDD. That was our first curve. That was this curve, right? When Vn went to 0.2, we were still essentially at VDD where they met. And now at Vn is at 0.4 VDD. Now we've got a little bit of a drop. Kind of like that. Okay, and then we keep going. Now Vn is a little bit, notice Vn is a little bit higher. Sorry, I'm superimposing this. Is there a way to erase it? Okay, sorry guys. How do I escape? Escape. Oh, good. I really don't like PowerPoint. I really don't like PowerPoint on my iPad. How do I escape out of this? I don't even know. Give me 1 second, guys. I'm trying to tap my way out of this. No. Great. Okay, I give up. Just give me 1 second to get back on this thing. Okay, let me try this again. So, but you guys see how this, what the story was. The point is that if I draw V in versus V out, as V in is going forward, V out eventually starts dropping. By the time V in is at 0.6, which was here, now all of a sudden look at where V out is. It's all the way over here. So it's all the way down here. Like 0.8, we're almost, the P is almost off, but maybe it is off. Let me look like that. VDD, it is totally off. So we get that transfer function. So did you guys see how that, as we're stepping through how we end up with that transfer function, you just look at where the different curves meet, the different currents meet, and you basically pick that drain source current and, sorry, where the IDS curves meet, or the I out curves meet, that's where your V out is versus that particular VN. Okay. So basically, again, if we transcribed all of them, we end up with a curve like this. So we pick a VN, and we see what that VN means here, say, and what VDD that corresponds to. When we pick that VN, I mean, like basically, what VDD that corresponds to, maybe, and so on, and then we plot this transfer function. Okay, everybody understands that? Any questions about that? Okay, so let's see. I think so. That's sort of the graphical, not sort of. That is the graphical way of getting the transfer function of a CMOS inverter. So let's look at this. Let me give you guys a couple of minutes to take a shot at this. So for each of these points, okay, for each one of these points, A through E, try to write down what operating region each one of these transistors is in, the NMOS and the PMOS, whether it's in cutoff, whether it's in saturation, or whether it's in linear mode. So why don't you guys take a shot at that for a couple minutes. I have myself on mute. Okay, guys, let's try to do this together now. So let's pick region, so A here. Okay, so Vn is low, and it's below the threshold of the NMOS. So that should be pretty easy. The NMOS is cut off. So the NMOS is off there. And the PMOS, so here N is is low, right? PMOS, so the gate of the PMOS is at 0. The source of the PMOS is at VDD. So the gate source, VGS of the PMOS is, that's pretty high. So it's definitely on, okay? But so it's on, so the VGS, the VGS of the PMOS is greater than its threshold. So it's on. Now let's think about whether it's in linear or in saturation. The output voltage, okay, the output voltage is VDD. So this guy's VDD. And so if I was going to draw this thing, so if PMOS had a curve like this, okay, so the output voltage is at VDD, and so the gate source voltage of this gate source voltage, sorry, the drain source voltage is low. So if you're looking at VDS versus VGS minus VT, the drain source voltage is very low because both the source and the output are at VDD. And the gate source voltage is relatively high. So that means that the VDS is less than VGS minus a VT. Okay, and now we'll put this guy at linear mode. Do you guys see how I got there? Any questions about that?
So when it's if the transistor, if it's considered on, it's going to be in linear all the time, or is it just?
No, so remember we basically had sorry, sorry guys, this thing is a pain in the butt. Just hold that thought for a second. Okay, so okay, so remember there was only one way for the transistor to be on. Sorry, one way for it to be off. And less than VT, it's off or cut off. But there was two ways for it to be on. Okay, so what turns the transistor on is the gate source voltage. As long as the gate source voltage is greater than the threshold voltage, the transistor is on. So both of these, the transistor is on. So it's pumping out current. Okay, then it has two. If I was going to draw it as a non-continuous, to just do a piecewise linear mode, it has two regions of operation then, once it's on. One is when VDS is relatively low compared to the VGS. So when it's less than VGS minus a VT, it's in this so-called linear mode. So it's on, and it's in linear mode. And then when VGS, that's over here, when VDS is relatively high, or as VDS is larger than VGS minus a VT, it's acting kind of like a current source. So it's still on, but it's in this saturated mode, so-called. Basically, the currents between these two are different because here the current is VGS minus a VT minus VDS times VDS, sorry, VDS over 2 times VDS. So that is IDS. Okay, so the current this current is a function, you see it being a function of what the VDS is. Okay, changes with VDS, even if I keep gate source voltage off, even if I keep the input voltage the same. And in this case, in the saturated case, the IDS is just beta over 2 VGS minus, minus VT squared, meaning that doesn't matter what the VDS does, I always pump out the same current. So it's like a current source. Does that make sense? So it could be, if a device, if a transistor is on, it could be either acting as a current source, in which case it's called saturated, or in kind of like a pretty nonlinear resistor with a square law component, and that's called linear mode, quote unquote. And so it depends on the drain source voltage. Does that make sense? So
Yeah. Also, I thought when you're using it for like a specific application, like in this instance, you're using it for switching, right? Because in like a digital circuit, transistors are always used for like switching.
yeah,
So isn't there like a linear or saturation mode? Ideally, it should be in one of them, right? It shouldn't transition to both of them, or does it
no,
just change?
you are trying to use this device. So, the MOS transistor doesn't know you want to use it for a logic type switching operations. It just knows what it does. And so, and it's a pretty non-linear device when you think about it, right? It's got this weird functions, it's got these strange VDS versus IDS versus VGS curves. So what we've done is we're using it as if it's a switch. So we're using it as if, where we started the class was, if this is a 1, then this guy's on, and if it's a 0, this guy's off. That's what you'd like, right? But the MOS transistor isn't going along with what you like. It's actually acting pretty differently, but we use it. So this is where we are. We're looking at how is it different? How is it acting differently than a perfect switch that's either off or on? So it will indeed go through all these in these regions while it's on, while it's switching, but we kind of like pretend like it's not. So, Tim, are you at like a CE or EE major? I'm just trying to figure out if you've done Verilog or VHDL.
Verilog Beach. Well, I haven't taken those courses, but I've worked with that on my own time before. So I've taken classes on this stuff. It's been a while also.
Sure. But conceptually, when you're in the domain of VHDL or Verilog, you're in the domain of zeros and ones. Whereas here in this class, we are trying to figure out kind of what's underneath the hood there. And, the reality is there's sort of some complicated stuff happening, but from a conceptual level, we'd love to just think of this as an inverter where you have, where you give it a quote unquote 0. Sorry. You give it a 0, you get a 1, you give it a 1, you get a 0. And that's what we like. We just like to think of it in that terms. But in reality, it's a little bit different. So sometimes if it's a properly designed inverter, you spend a bunch of time designing it, like doing what stuff we're doing it now. You stick it in your library, and after that, if it has enough noise margins, if it's fast enough and so on, you just think of it as this device. After that, you just think of it as 0, 1. You don't every time you use the inverter, you're not thinking in terms of currents and voltages, et cetera. You just sort of do that once, and then you basically use it as a higher level of abstraction than we're doing now. Remember that sort of the abstraction plots? So, the highest level of abstraction is just, the crystal lattice and device physics, semiconductor physics. Next level of abstraction is the transistor with all its glory of, voltages and currents and these transfer functions like we're doing now. And then you can take it to the next level of abstraction, assuming you've got a good design of just ones and zeros. And then, you keep going up in levels of abstraction until we're just dealing with it as if it was, a C program or something like that. Does that make sense, what I'm saying?
Yeah, basically it gets more complex, deeper you look at it.
The deeper you look at it, but if you try to design a 54 billion transistor chip, thinking about every single transistor's current versus voltage versus this versus that, it'll take you 54 billion years to get that chip done. So what people do is they go through and they design a library of parts using the analysis kind of thing that we're doing now in simulations and so on, and then use it at a higher level of abstraction as if it was a switch. As you go further up in abstraction, again, when you go up to, you guys know better than me, I haven't programmed since I was an undergrad, but if, when you're doing programming in C, you don't even really think of in terms of inverters or non-inverters, you're thinking of in terms of like if-then loops and stuff like that. And it's even, much higher level of abstraction. So I don't know, that's probably a little too much more than you asked, but it's really not a switch. We use it as a switch. We try to pretend, like when you're in lecture 2 or 3 or whatever in this class, you're pretending it's a switch. But now we're kind of looking at the ugly reality under the switch and seeing how that affects your noise margin, et cetera. So that was a long answer to your question. Does that make sense, Tim?
Yeah, that makes sense.
Okay. So anyway, we'll go through all these modes. So again, in B, in region B here, the input is higher than the threshold at the end. So now the NMOS is on, okay? The input is lower than the threshold of the P, so the PMOS is also on. So both of these guys are on, N and the P are on. So now the drain source of the N, which is the output, that's relatively high. So if I look at this B here, the drain source of the N is close to VDD. The gate source of the N is low. I don't know, it's close to VT. It's a little bit higher than VT. Okay, it means it's on, but it means that drain source of the N is greater than VGS minus VT of the N, which puts this guy here, the N at saturation. Okay, and if I look at the P, it's an on, but look at the drain source. The drain source of the P is, still, it's basically at VDD, what is it, like maybe 0.9 VDD minus VDD. So it's pretty small. So the drain source here of the P is smaller than the gate source minus VT. So the P is in linear mode still. Okay, so then right at C, now you've got a case where the drain source is greater than, basically drain source and gate source. Right at C, V in is equal to V out, right here. or close to it. So the drain source is equal to the gate source, but that means that the drain source is greater than V gate source minus a VT. This part, we're subtracting a VT. That means those two things are both in saturation. Okay, and then I won't do this part, but it's the opposite of this part as far as the NMOS and the PMOS are concerned. So here, NMOS ends up being in linear, and PMOS ends up being in saturation. And then NMOS stays in linear, and PMOS finally turns off. Okay. So Tim, to go back to your question, if this was a perfect switch, you'd kind of end up with something, not kind of, I think you'd end up with that, basically. So, you know, basically where we are looking is how are we different than this square transfer, or not a square, but you know, the step transfer function, and how does that eat into our noise margin? Yeah, that's what we're doing, depending on the sizing of our devices. So that's the purpose of the analysis. Okay. Any questions about that, guys? Okay. So again, you just basically, you can size these different things. And if you notice, by sizing things differently, so this is assuming that we size them so that the beta of the N, we started with the assumption that beta of the N is equal to beta of P, or the width of the P's transistor is twice the width of the N transistor. These were like sort of assumptions when we started. So this sucker switched right at the halfway point. Basically, right at the halfway point, the currents were exactly the same. Drain source VGSs were the same, right? But this doesn't have to be the case. And if you change those ratios, you basically start moving around where this shift happens, where these regions happen. So this should be beta of P over beta N. And it should be beta P, beta of N. Means that the wider you make your device, the later it would switch. So the higher input voltage you need before it'll get a zero. So here look at what you're doing. So you switch this over, means that this is your input 1, and this is your input 0. Okay, so you're like, and then vice versa. Here, when you've made the P much narrower, here is you've made the P much narrower than the N. You've made this the equivalent, from an input standpoint, you've made this the equivalent 0 and this equivalent to 1. So you're screwing up your noise margin of, depending on which one you do, you're either degrading your the noise margin for your 0 or your noise margin for a 1. Okay, so that's how it goes. And then basically the way you calculate, but the idea behind the noise margin is, let's say you have two inverters, two exactly the same inverters driving each other, or one is driving the other, sorry. So basically there is a permissible, so if you look at just the output of this first inverter, there is a permissible range of high output values and low output values. And there's if you look at this inverter, it has a permissible range of input high and input low values, where we recognize a logic low and a logic high. And the noise margin is basically the difference between the lowest possible output high, between the lowest output high and the lowest input high. Okay, that's your noise margin, and the bigger it is, the better, and vice versa here. So by basically moving stuff around, by moving this curve around, you're basically changing which, whether it's a 1 or 0, that would have a worse noise margin. Okay, so you've given each side a 0 or 1, the same noise margin if you're right in the middle, and it would shift one or the other if the sizes are not ratioed exactly, not ratioed so they give the same current. Does that make sense? Okay. And so, and also we're defining
actually that on that other slide.
This one?
Can you hear me?
Yeah, I can hear you, Tim.
Oh, okay. So on that slide, that region, that the indeterminate region, you want that to be as big as possible, or you want that to be as small as possible?
You want it to be as
big,
small
right?
as possible. You want it to be as small as possible. You want basically the input high to kiss up right against the input low. So ideally, you'd want it to be here.
Oh, okay, so there's a clean switch between on and off.
Yeah,
okay.
The ideal thing is like that, where the indeterminate region is 0. There's no, you're just going immediately from one to the other. Because remember, the noise margin, your output from the previous stage is up here. So it would have to get a lot of noise on it before it gets mistaken. The narrower that intermediate region is. Okay.
Doesn't the noise margin mainly deal with or the manufacturing of the actual transistor itself? Or is it not determined by that?
I mean, I guess in some sense it does. So what the manufacturing of the transistor does is it gives you these curves, right? The P and the N curves versus, your supply or gate source voltage, or 1 and 0. Now, you could, when they manufacture, if you remember from, let me see if I can do this without pulling everything up. So if you remember this slide from the previous lecture, basically the manufacturer has some variability in how they manufacture the stuff. And maybe this stuff makes more sense now, because look at what's they're saying, what can change is the threshold voltage, Tox, L effective. All these things are changing our IDSs for N versus P. Okay, from chip to chip, from wafer to wafer, from wafer run to wafer run. So you're getting this variability, meaning that if you design your chip to have exactly, you started with some assumption that I'm gonna make with these transistor sizes, and this behavior of the transistor, I'm gonna make beta N is equal to beta P, and put my switching point right in the middle with just with variations in manufacturing. You're gonna switch one way or another, and you're gonna degrade your high or low noise margin depending on that particular iteration of the chip, or that particular physical implementation of the chip. Does that make sense?
Yeah, that makes
Yeah.
sense.
So as a designer, you have control over the noise margin. You end up designing it for the typical case or for the nominal case. And then you have to simulate it. And then the other stuff, the other stuff is we saw how temperature also changed current versus voltage. And power supply changed current versus voltage. And all those things are changing your betas. So it's the manufacturing, it's the temperature, it's the power supply. All of them are affecting your noise margin. Some of, the temperature and power supply actually is sort of a dynamic change in your noise margin. So you could have a worse noise margin when things get hotter or colder or something like that. Does that make sense, Tim?
Yeah. If you can't hear me, it probably means my internet connection is terrible.
Yeah, I'm in the same boat.
It keeps saying like unstable like every 4 seconds. So I don't know what's going on.
Yeah, we should compare notes about which routers and which providers we're using.
Don't use Frontier. That's all I know.
Okay, well,
Frontier, other than FiOS, Frontier is terrible.
I see. I hadn't even heard of Frontier. I'm using Spectrum. But, see, Frontier is already warning you you're in deep crap, right? You're on the frontier. Internet can't be good on the frontier. So anyway.
Well, should have saw that one coming.
Yeah, move out of the sticks, Tim. Or I should too. All right. So so anyway, so the way we define the point where we go from from the minimum input level, okay, so where the transfer function for our noise margins are, is when our transfer function curves go to a slope of -1. So this is a curve we drew. The slope here is pretty low. The slope here is very high. And, we had to pick a number. Then we pick -1 as our demarcation point. Okay, and why is that? Well, going back to, I think early on in the class, we said that one of the key things about the logic gate was that you needed it to have gain. That means if you had sort of a bad logic level, as long as it wasn't too bad, you would get the logic level restored. I think we called it restoration or restoring. So this logic gate would restore the level to, you can't have it be too bad, but if it's basically making it better, so good logic level. And if this wasn't the case, then what would happen is, if it was the opposite case, where you'd get a bad logic level and your transistor would just make it a little bit worse, as you string up your logic, basically, your signal would just die, right? So you'd have sort of a iffy logic level here, and you'd end up with like complete garbage on the outside. So you need this function, right? So if you have a slope of V in versus V out, which is greater than -1, means if there's any noise on your input, it gets amplified. So here, between a -1 and -1 points, here, your inverter is actually kind of like is an amplifier. It has a gain, typical gains you see without trying too hard, maybe a gain of minus, I don't know, -5x to -10x. Or you can make it higher if you want to act like a You know, some people use these as analog amplifiers. They don't make very good analog amplifiers, but you know, in a pinch. But look at, this is sort of a bad situation. If you have noise on your input, you're amplifying that noise on your output. So basically you want to stay away from this region and you want to be here and here. So you define it at the where you go from to a -1. Past -1, past here, you're getting a higher than a gain of 1, and you know you're at every layer of logic, you're increasing the amount of noise you have. So anyway, that's how we define it. Okay, so that's it for the transfer function and how so you guys saw by changing the relative widths. So you know, theoretically speaking, the ratio you're changing is width over length, but length reduces the current of your NMOS or PMOS. So it reduces the current, but it increases the gate capacitance. So it's just people don't do that in logic. They just keep the lengths at almost every case. Very rarely do in logic you see the lengths of a transistor higher than minimum. Sometimes you see it, but rarely. So basically you're playing around with the widths. And by adjusting the widths of your N and P-type transistors, you can optimize the noise margin for your gate. Okay. And before we leave this, so this is what we did for an inverter, but notice the situation for a NAND gate or like a gates is similar, but it can get a lot more complicated. So let me just show you guys that just as a aside kind of thing. I think we'll see that later, but let's say we have a NAND gate, right? Like you can use the same analysis for a NAND gate. So let's say we want to figure out the same VN versus VOut for a NAND gate. Well, the problem is for a NAND gate, you have two inputs. And so what happens with a NAND gate? I think it's 0, 1, 1, 1. Right? So the problem is there's more than one way to go from a 0 to a 1. Right? Notice that when I go from a 0 to a 1 here, I only have, a 0 always has both of these guys on, right? Okay, so you always have the same beta N essentially, regardless. But the beta P depends on whether you're going from here to here or here to here. Here you have two PMOS transistors in parallel turning on. Here you have one PMOS transistor turning on. So the effective width, the effective beta P here is twice this beta P. So depending on which input's changing, if you're going from 1, 1 to 1, 0 or 1, 1 to 0, 0, you'll get a different, you know, the noise margins will be different. So, and then same goes for a NOR and the N MOSFETs. Depending on whether they're both on or just one of them on, your noise margin will be different. Okay, so just another complication of, you know, how you're non-ideal, say, compared to a switch. Okay, So, how are we doing? It's getting close to our 8:15. So that's where we stop with the transfer function. And then when we start again, we have the midterm next Tuesday. So next Thursday, I think I'll start talking about the transient response there. And again, the transient response is how by designing the different sizes and so on, if you have basically response with respect to time. So if your input looks like this, does your output look like this, or does it look like that? Basically, how fast are you switching and at what cost? Okay, guys, any questions?
Professor, so are we gonna have lecture on Tuesday, or do we just directly go to the test?
It just goes directly to the test. So I'm gonna put it up put the midterm up on Blackboard at 7 p.m. and you guys will have till 7 p.m. on Wednesday to email it back to me.
And which email do we use? Is it on the one that on syllabus?
Yeah.
Okay. Thank you, Professor.
Sure. Any other questions?
So, do you have any office hour this week or?
Yeah, I'll have office hours at 4 p.m. tomorrow. So I'll have a Zoom session up. And then I'll have also office hours on Monday at 4 p.m.
Thank you.
Sure. Any other questions, guys? Okay, if not, have a good weekend. And yeah, just let me know if you have any questions. You can always, if you can, make the office hours or whatever. I'm not really doing anything this weekend, so feel free to email me, etc. I'll keep an eye out on emails to if you have any questions. All right, guys, have a good weekend.
You too, Professor. Thank
Have
you.
a good one. May the internet gods be in your favor.
Yes, thanks, Dan.